Yeah, okay, I'll start. So, on Monday I talked about the product structure theorem and mentioned an application. So let me state the theorem and then do a couple more applications so that you can see what it's good for and perhaps be motivated to stay awake. So, product structure. Which I've probably stated more than once before. It says this, given our manifold M, usual dimensional restrictions, M should be greater than or equal to 5, or if the boundary is M is not empty, then M greater than or equal to 6. And suppose there exists a cat structure, cat inverse PL or diff, either one, a cat structure, let's say capital sigma on M cross R, and suppose there exists and suppose sigma equals little sigma cross R on a neighborhood U of closed set C, it's always closed and compact, of C inside M. So in other words, we're supposing that we're trying to get this PL cat structure on M cross R, trying to get it down onto M cross 0. So we suppose that's already done on this neighborhood of C. So here this is little sigma. It's just a little sigma because it's on a lower dimensional, it's on M cross 0 instead of on M cross R. So little sigma. So this is the cat structure on M cross 0. Well, not on M cross 0, it's on a neighborhood on U cross 0. So that's what that means. Given all that, then little sigma restricted to a neighborhood of C extends to a cat structure on all of M cross 0 if you wish, and sigma cross R, that's the cat structure just crossed with R, is concordant, which is still related, concordant to capital sigma. This is, of course, on M cross R. So that's the conclusion, that you can, this is just a relative version. If you ever forget the relative version, and it just says if you've got a cat structure on the M cross R, you've got one on M. So that's what that says. Now, so how was this used? Well, the easiest one to do is handle bodies. And I sketched that last time. And actually, there's not much more to than just a sketch. It's pretty easy. So there exists a handle body structure on M if the dimension of M is not equal to 4, and sometimes not. Well, here's this. And in dimension 4, M is a handle body if and only if M is smooth, is diff. which is equal to PL in dimension 4. So let me actually get dimension 4 out of the way first. It's a different argument. So in dimension 4, it's known that if a manifold has a PL structure, it has a smooth structure. And there's not much difference between the two categories in dimension 4. That uses old work of Serif, and anyway, it's a complicated argument, but this is true. By the way, I should make the remark at some point or other, just sort of a philosophical remark. So here's a parenthetical remark. The difference between PL and diff, those two categories, smooth manifolds, PL manifolds, is that one can take cones in PL, but not in diff. And not always in diff. That's kind of a philosophical slide.
That's why there are no exotic spheres in PL.
That's right. So, in PL, if you have a PL homomorphism of a sphere, so it takes simplices to simplices, it kind of does something to the sphere, you can take the cone. And so every time you have a simplex out here in the sphere, you just cone it into the center point, and then it's a one higher dimensional simplex. And so if this edge goes to this edge, then you just take this cone to this cone. So that's, you can take the cone of PL homomorphisms, but that doesn't work in the smooth case. It doesn't even work for circles, because think of taking a circle where you take the upper half circle and stretch it down, expand it, and squeeze the bottom. Well, then when you cone that, this thing goes to this. You got a corner. So you can't even cone a diffeomorphism of a circle. And that's really the difference between these. The exotic 7 sphere is made by taking an interesting diffeomorphism of the 6 sphere and you glue together the two halves. And if you could cone, then you'd take that interesting diffeomorphism and just cone it, and you'd get that the exotic 7 sphere was standard. But you can't cone. So that's a comment about that. So anyway, but in dimension 4, those are the same. But now suppose, so first of all, if M is differentiable, then it's certainly a handle body. So that part is very easy. For this part, notice that if it's a handle body, how do you make a 4-dimensional handle? Well, you start off with the 0 handle, which is a 4 ball, and you attach a 1 handle. Or you attach some handles. But whenever you attach, you're attaching them to the boundary, which is 3-dimensional. And every 3-dimensional manifold is smooth. Well, what I'm going to claim is that if it's a handle body, it's smooth. So the 0 handle is smooth. Now when I attach a handle, I'm embedding the boundary, which is a sphere cross whatever. It's a 3-dimensional boundary, and you're embedding it in the 3-manifold. Well, it's 3-manifold theory. It goes back to, I suppose, Moise and Big around 1950. It's a 3-manifold theorem that any embedding, topological embedding, can be isotoped to a smooth embedding, because you're in dimension 3. So then that attaching handle is isotoped, and now the smooth structure extends over it. And you just keep going handle by handle. So if this is a handle body, the point is that the interesting part about it is the attaching maps, and they're happening in dimension 3 where everything is smooth. And so it's a handle body, then M will be smooth. So that's what happens in dimension 4. And then of course we didn't know there were 4 manifolds that weren't smooth until Donaldson's work. But now that we know that there are, well, that's a long story, but anyway, there are 4 manifolds which are not smooth, and therefore not handle bodies. But in every other dimension, I'm talking about closed ones here. If it's a manifold, all right, so let's say if the boundary of M is 4-dimensional, well then, we can add handles. To boundary M to get all of them. Now, I'm not, I'm worried that's too strong. Because after all, we're not claiming this theorem, or I haven't claimed it so far. Oh, you forget these things. And I didn't focus on this problem before I started here. The way this is being stated is that if M is 5, yeah, so,
Just
yeah, I
worry.
don't know.
Let's just worry about the
We'll
high
worry about
dimensions.
this later. We'll
Yeah,
worry about
let's just
this
worry about the
later.
high dimensions, which
Yeah,
is
we'll worry
the
about that.
key.
So, how do we prove this in say, dimension 5 or above?
Exactly.
So the way to do that is just what I mentioned last time. So you start off, start with a chart in M, which, because it's a chart, it's homeomorphic to Rn, so which is a handle body already. So, I mean, it's an infinite handle body because it's Rn, or Rm. So take a large compact piece of it. So we're gonna cover, I mean, behind all this, I don't tend to say this each time, but behind all this is that you have a cover by charts and a subcover by compact subsets of the charts. So not only do you have open charts covering, but then you can take a refinement by compact pieces and they cover. And you can actually do even further parts of that. You can keep refining if you want to. But so you have these compact subsets, and these compact subsets are going to be inside the handle body. So we start with the chart. Now then we look at the next chart. So here's the chart that we just did. And it has a compact set you know, this part, this is a compact handle body right here. It's as big as you want, but it's compact. Now you take a new chart. So this is a new chart. And you look at, so it's got a smooth structure. It's a chart. And inside of it, we see this bit of the boundary of the handle body that we're looking at. So this is the boundary, which is the boundary of the handle body we've already constructed. It's the yellow part's what's inside the new chart. Well, so this, remember, this was a compact handle body. It certainly had a product neighborhood. So this is some boundary piece cross R. So this set is some manifold, say L cross R, where L is this yellow part. So that is open. That's open inside this new chart. So L cross R gets in this case, let's do the smooth case, the smooth structure from the new chart. So might as well call that our structure's capital sigma. Well, now then, product structure theorem implies that so there implies that there exists a diff structure, a little sigma on L, and sigma cross R is concordant to capital sigma. Well, so what does this mean? When you're thinking about this, you can think of L as a smooth, well, it's a manifold, topological manifold, and crossed with R, and it's embedded in there. And so it picks up it picks up a smooth structure. The product picks up a smooth structure, and now we can think in two ways. We can think that this smooth manifold L cross R what I'm trying to say is that I want to think of this. I want to think of L cross 0 as a smooth manifold inside this chart. So how can we think of it as a smooth manifold? Either it's not as it stands, so either you have to wiggle L to a smooth embedding, that's fine, or you can wiggle the smooth structure on the chart. You can change the structure so that the L as it stands becomes a smooth submanifold. Either one of those will do, and they're equivalent. They're just sort of two ways of thinking about the same thing. So let me explain that a little more, because it's kind of a piece of intuition that often doesn't get explicated very much. So if I, for example, so let's just take a smooth case. If I have an arc, it's embedded, and it might be embedded as that in the plane. Sorry, I don't mean that. I mean, you don't want to say it that way, I want to say it the other way. I got a PL arc, so here's my PL arc, and it's embedded this way in the plane, so it's not a PL embedding. So I have two choices. I could isotope it, so I could sort of go down like this, up like that, and over, so that it moves to a nice rectilinear thing. I could do that, or I could change the triangulation on the plane. I could change it so that this is a simplex. There's a vertex, and a vertex, and a vertex, and a vertex, and then maybe this triangle has got a curved side. And it's just part of some of the sides are going to be curved. Well, that's a PL structure. It's just not the rectilinear one that's normally associated with the plane. It's just, you look at the triangulation of the sphere. Well, the triangles there, they're curved sides there, but they're still triangles. When you think of the sphere as the boundary of the tetrahedron, well, then all the sides are straight in some sense. Or you can think of the regular Earth and draw longitudes which are curved. And it's all sort of the same. So you can either think of changing the smooth or PL structure so that the embedding was now PL, or you can think of moving the embedding so that it becomes PL in the old triangulation. They're both the same idea. So here, I think the easiest way to say this is that let's keep this the way it is and change the differential structure on the chart. And now if you're going to change it, you don't want to change it everywhere. You just want to keep it the same, and then in this little collar neighborhood, you begin to change it across a little bit of the collar, and then that becomes smooth. So whichever way you think of it. Now that this is a smooth submanifold of the smooth structure here, then I don't know, just do whatever you want to do. pick a Morse function on which this is a level set, and then extend it using the product, and then extend it to just any Morse function. You can always do that, that's just an extension theorem to the reals, you can always extend functions to the reals. And perturb it and make it a smooth function. And then, once it's a smooth function, then you do Morse theory, you've got critical points and critical values, and they correspond to handles. So once this is smooth, then just ordinary smooth theory tells you that you're mapping to the reals, you get critical points, some of them are one handles, which are attached like that, some of them are going to be two handles, which I can't draw on the blackboard. Anyway, you extend handles out here to cover as large a compact piece as you want, so that you have a finite number of handles, covering as much of that as you want, and then you go on and on, more and more charts, until you're done. So that's how you put handle body structures on. And it's simply this little argument here with the product structure theorem that enables you to do that. So that's handle bodies. Now the same thing works for transversality. So for transversality, the kind of transversality one wants to start with is, so this is transversality. And it's going to use this product structure theorem exactly the same way. So for transversality, we start with a map from F, from a manifold to the reals. And again, there's a relative version, but it's never a problem. So we say that F is transverse. You have to say what topological transversality means. So F is transverse to 0, the origin in R, if F inverse of 0, well, suppose it was a smooth map, and that was a regular value. Well, then F inverse of 0 would be equal to a manifold L of dimension m minus 1 with a normal line bundle, let's say epsilon 1, so that F restricted to L, well, I'm thinking this line bundle is embedded, so it's really L cross R. That's the line bundle. Then F restricted to L cross R, mapping to R is what's called a microbundle map. To the bundle R over a point. So there's, I'm thinking of R is just a line bundle over a point. And so here we have, you can set this up various ways, but here you have, in transversality, if this is smoothly transverse to a point, then you have that point has a normal line, and that line gets pulled back to a normal factor all along this codimensional one manifold. Well, the same thing is true in the topological case. So your picture is M mapping by F to R, and there's 0. So here's L, and it's got this nice little bundle, and it goes to all of these normal lines go to the neighborhood of that. Don't be confused by this microbundle map. All I'm saying is that this copy of R, which you see as a sort of a two-to neighborhood, these are copies of R. They don't go on to all of R. It's just that locally there's a perhaps smaller neighborhood which goes to a small neighborhood of R, of 0. But, the difference between R and a small open interval is not very much. So that's what it means to be transverse, and the theorem is that F is homotopic to So given just starting off with sub f, and f is homotopic to a map transverse to 0. Plus a relative version. You know, you've seen so far these relative versions always just come for free practically. So f is homotopic to a map transverse to 0. And, well, it's no surprise, I mean, look at this picture I just drew, and look at this picture, you can sort of see it's the same, going to be the same kind of argument. So it's a chart by chart argument. So, so I'll pick a new picture here, but it's almost the same picture. Here's M. Here's a coordinate chart. So in that coordinate, that's a smooth manifold. So make that transverse to 0, and you get a submanifold L, and here's its normal bundle. You can do that on the chart because the chart is already smooth. Now take a new chart, and in this new chart, you have a smooth structure, so you alter the smooth structure so that this is our yellow piece again, same argument, same philosophy, just hardly any different. So this was smooth in the old chart with a nice normal line bundle. So it's smooth in the old chart. So now wiggle this smooth structure so that this is a smooth submanifold in the new chart. So now you have a smooth structure on the new chart in which this is a smooth submanifold with a nice little normal line bundle. And now use relative smooth transversality to wiggle the map on the rest of this chart and extend the smooth manifold over the rest of the chart. You might pick up new components, who knows? I could have a new component. Anyway, you extend it by the smooth case, and now you've got this over this chart, and you go chart by chart until you're done. So it's really very similar to this argument. Now you might ask, well, that's fine for maps to the reals, but what about maps to something more complicated? Well, I won't go into too much detail on this. But if you're mapping from M to RS, and you want to make a transverse to 0, it's the same game. Because after all, the product structure theorem works for, well, I didn't state it, but it works for RS, because if you have RS, then you split off one factor and you push this PL structure, cat structure down to RS, M cross RS minus 1. And then split off another R and another R until you get down to M. So you had the product structure theorem for a structure on M cross RS. And then, now if you're mapping to RS, you have a chart, and you get your manifold L, and now it has, it has a normal plain RS bundle everywhere. And you use the product structure theorem, and again you make M cross 0 into a smooth submanifold, and you just do the same thing. There's no more to the argument. It's just you do the same thing. So this is the RS bundle over point. Well, that's not quite as much as we want. We want to actually have transversality. Want transversality. For M mapping to an Rn bundle over a space X. This is just a topological space, it doesn't have to have any more properties. Just a topological space, and this is an Rn bundle over. So E is not even E and X are not even manifolds, but the fibers are Rn. And you know, for such a bundle, the fibers are simply glued together by homomorphisms which vary continuously over this topological space, which has a topology, open sets. And so how do we do this? Well, you work, so to prove this, I'm going to let you, if you want to follow further, read the proof in essay 3 of the book, Analyst Study Kirby8. So I will just sort of indicate what happened. But the X doesn't cause a problem because locally, you do this on charts in M. So you work, you know, just as we always have, you work chart by chart in M. And the charts can be small. So you pick charts, you subdivide, pick refinements, pick charts small enough so that is a map F restricted to a chart lies in a local trivialization of this bundle. Bundles often called C. Exemplary bundle, i.e. F maps the chart into U cross Rn, mapping down to U, where U is simply some open set in X where the bundle's trivial. Because bundles have to be locally trivial. So you're just mapping into this. And then you can simply compose by projection out of the second factor, you can map to Rn. And now we just did transversality as a map to Rn, and this U is simply a dummy factor. What you're doing is you're homotopping the map into Rn. So this map F used to have two coordinates. It went to, F consisted of a map to U and a map to Rn. It was a pair. And it's the second pair that you're homotopping and making transverse. And then the first one doesn't even have to change. So we don't hardly care at all what U is. So you make it transverse in that way, and you work chart by chart, and so on.
It's quite different from the differentiable argument.
That's true.
That's the crucial
Yeah.
thing. It's much harder.
Yeah.
I mean,
And now finally, the last remark to make, you know, usually you think of transversality, you're always often thinking of a pair of manifolds inside a larger manifold. And they're not transverse, but you can wiggle one of them so that they become transverse. And then you get an intersection, which is a yet still lower dimensional manifold. So that's how you, that's often the version of smooth transversality people use and think of. So how does that work here? Well, the theorem is not known in quite that generality, because in the smooth case, each of these embeddings, it may not be transverse yet, but each embedding has got a normal bundle, because in the smooth category we have normal bundles. But in the topological case, these topological embeddings don't necessarily have normal bundles. And without those normal bundles, it's not clear what happens. But if one of them has a normal bundle, so if, let's say, if MM and NN are topologically locally flat, no, just topologically embedded in Q, dimension Q, and if one of M or N, let's say M, has a normal bundle, say nu sub M, then we can perturb, in other words, a small, arbitrarily small motion, we can perturb the embedding of M to be transverse to M. What's going on is that here you see N, this is N sitting inside the blackboard, which is Q, and it's got a normal bundle. Doesn't have to be trivial, but it's got a normal bundle. And then here comes F wandering along, and it's, does whatever it does. It's not necessarily, this is M, the embedding, it's the image of M. And it's not necessarily transverse to M. But you use local trivializations. There's a bundle here. In fact, well, what's our situation? X is now N, and you have an R, and you have a bundle over it. So up there, N takes the place of X. And now this is a map. We're not interested in where this embedding goes out here. We're just interested in making it transverse to M. So we're working inside this bundle. And now you have a map. You have M's embedded here, but it's a map into this bundle over X. And so you use that transversality to wiggle M so that it becomes transverse to M, all working inside this normal bundle. And now the new intersection would be this. This is your L, and L has a normal, L itself has a normal bundle in M, which projects onto the fibers of the normal bundle of N. It's of that dimension. So the transversality of submanifolds works fine as long as one of them has a normal bundle, and we can do this process. But only then. If it doesn't, then well, there's probably something known, but
what are the general conditions for a submanifold in the
bundle.
topological category to have a normal bundle? I mean, of course, it's lifting.
Well, first of all, you need M to not be wild.
Locally flat.
Yeah, it's got to be locally flat. So let me state a couple of things. I was going to tell you more about bundles another time when I look up all the relevant cases.
Well, let's put it another way. Can you give an example of a locally flat embedding which doesn't have a normal bundle?
Well, they occur in dimension 3, codimension 3.
Mm-hmm.
So the collaring theorem from way back says that codimension 1 locally flat, well, theorem was locally flat implies flat, and this implies there exists a normal line bundle, or one bundle. codimension 2, locally flat. This implies in all dimensions that there exists a normal two-plane bundle. And this has an incorrect proof of mine in print, so don't pay attention to that. But then it has a correct proof that Larry and I wrote down for avoiding dimension 4, for something or other, whatever it is, not equal to 4. And then Quinn, in his work after Friedman's work, Quinn proved it for the rest of the cases. So, yeah, when the manifold is of dimension 4 and is embedded in some 6-dimensional manifold, Larry and I didn't know what to do, but Quinn fixed it up. So that's the codimension 2 case. And then counterexamples. Exist in codimension 3 or more. And I suspect they exist, I think, in the PL case, in that, and so that would be an example. But I don't have a reference for you at this time.
I think Brown Sanderson,
Yeah.
early, late 60s.
Sanderson, yeah, right. So you don't always have these normal bundles. So that's sort of a defect. There are other things you can use. The PL case are block bundles, in the topological case there are topological block bundles. So that's transversality, and from transversality you can get topological Morse functions. Or a topological Morse function just says that if you have a Morse function, if you map to the reals, on some charts it's just projection, and in other places there's the equivalent of a critical value, and what it means is that topologically there are coordinates that it looks like a smooth function with a critical value. So there's no surprises there, and that follows from transversality. So topological Morse theory is okay. Well, it's okay if you avoid dimension 4. Because if you had topological Morse theory, you'd have handle bodies. So, well, yeah, I should say this. So, back here when we're doing transversality, the theorems I've stated, transversality works in all dimensions. So Larry and I just did it with the product structure theorem, avoiding dimensions 4. So in transversality, you have to be sure that you're not going to try to get something of dimension 4, and you can't have the domain be dimension 4. There's two things to avoid. And those were worked out. By, well, Frank Quinn is the main person to mention. After Friedman did his stuff in dimension 4, in various ad hoc ways you could get transversality to work when the manifold that you're trying to get is dimension 4. And when the domain is dimension 4, something else works. So this is just what you should remember. And then you have to look, if you want one of these strange low-dimensional cases, you have to look up some papers.
There's a paper by Alexis Marin,
Yes,
who was a
that's
student of Larry's.
That's
It's
right.
in French, so not yet been discovered in the West.
I should remember him, Quinn, and Charlemagne had something,
Yes.
did something in his thesis.
Yes.
So a variety of people put things together there.
I'll dig out the references.
So transversality works in all cases, but not topological Morse theory, because usually Morse theory implies you get handle bodies, and you don't in dimension 4. So you have to be careful assuming about what's true and not true in dimension 4. Hard to remember all the little
Sure.
little glitches with it. Now then, well, I might as well do one more application. And that is to finite type.
Simple homotopy type,
Yeah,
not the modern use of the word finite.
yeah, simple. So, any topological manifold has a well-defined simple homotopy type. So this depends on you knowing what simple homotopy type means. So we've got about 10 minutes, so you know what a homotopy type is, just from homotopy theory. And simple homotopy type, well, that started, I believe, with J.C. Whitehead in this long, impenetrable paper he wrote around 1940.
Nuclei.
Nuclei, yeah, nuclei is part of the title. Yeah. So the idea there is to go back, assume that things are simplicial complexes. So if you have two simplicial complexes, and let's say you have K and K prime, and you have a map from K to K prime, you could ask whether, let's say it's just KF going from K to K, and so we already know what it means that F is homotopic to the identity. The identity map, which of course is simplicial, and then you know what F means for F to be homotopic. But F is simple homotopic, SHE, simple homotopic, to identity. So how do you do it? Well, so then the idea is you have elementary expansions and collapses and subdivisions. So if through subdivisions and elementary collapses and expansions, one can move F to the identity. So an elementary collapse, you have a simplex, you have to have a free face. Let's say this one's free. Then you just collapse. You collapse it down to this. That's a collapse. And an expansion is the reverse. If you see that, you put in a simplex. And you can subdivide. So that gives you a homotopy, because after all, just pushing this in is a homotopy. You can see it going in. That's a homotopy. And expanding back out, that's a homotopy. So these are this is a nice kind of homotopy. And
Simple homotopy.
it's a simple one. Yeah, so that's a simple homotopy type. Well, so then not all things which are homotopic are simply homotopic. So if pi 1 is 0, then homotopy equivalence implies simple homotopy equivalence. But when pi 1 is not equal to 0, then it's not necessarily true. And this is lots to say here, but you've heard of the H-cobordism theorem and the S-cobordism theorem. Well, for the H-cobordism theorem, that's in the simply connected case, and you assume this bordism is a product, homotopically. But If pi 1 is not 0, then there are cases of H cobordisms where the manifolds are not simply connected and it's not a product, there's an obstruction. It's in the Whitehead torsion of the fundamental group. So you have to assume that this thing is a simple homotopy equivalence, and then it is a product. And that's the S in the S cobordism theorem. You have that in additional fact. You have to have something that's equivalent to this notion that this is really Whitehead's notion, and by introducing the Whitehead group of the non-trivial fundamental group, I mean, sometimes an H cobordism is enough because in some cases the fundamental group is so simple that you don't have any obstruction.
You can do Gaussian elimination.
Yeah.
Basically.
Yeah. Yeah, there's another whole lecture or two or
No, not
around
now.
it.
It's okay.
So anyway, so there's that. And so one of the big conjectures in the 60s was if you had two complexes and they were homeomorphic, not just homotopy equivalent, but if they were homeomorphic, then did they have the same Whitehead torsion? Did they have the same algebraic obstruction? So the pi 1 might be non-zero, but yet the complexes were thought to be homomorphic. So this was the topological invariance of Whitehead torsion was the issue. And so that is true, and that follows from, it sort of follows from this. When I say it's a well-defined simple homotopy type on M, that means that if M is homeomorphic to two different triangulations, two different simplicial complexes, then they're simple homotopy equivalent. So what's the well-defined in this part? Okay. So what is it? Well, yeah, I'll just go ahead in a couple of minutes. So you embed, so here's the factors that haven't been proved yet. Embed M in a high enough RQ so that M has a normal bundle. So that's important. So I've said over here that not everything has a normal bundle. You know, co-dimension 3 or more. But if you stabilize, if you add extra dimensions, then you always can get a normal bundle. So topological manifolds stably, you do have nice bundles and so on. So embed it in a high enough so it has a normal bundle. Well, actually, and in fact, a normal disk bundle. That does not necessarily follow. There are topological normal bundles whose fibers are in, but the unit disk is not preserved and can't be preserved. So not every topological normal bundle has a disk bundle inside of it. However, if you stabilize some more, it does. So that's because, you see, if you have a normal vector bundle and the structural group is ON, well, an element ON preserves the unit disk. So you have a unit disk bundle inside. But if you just have a normal bundle where the gluing maps are just homomorphisms of Rn, that doesn't automatically preserve the unit disk. It just moves it around. And it turns out that there are normal bundles where you can't reduce to the subgroup of the homomorphisms which do preserve the unit disk. You can't do that with bundle reduction. So, but if you stabilize enough, you can get a normal disk bundle. So now, the sphere bundle, that's the boundary of the disk bundle. The sphere bundle is codimension 1 in this high dimensional Euclidean space, high enough, and that it has a normal R bundle. It's codimension 1, it's got a normal. You've got the sphere, so there's all these little lines in the sphere. So it's got a, so that's open in RQ, so it has a smooth structure, so you apply the product structure theorem. So you wiggle either the smooth structure in RQ or the embedding. You wiggle so that the sphere bundle is, let's say, is PL in RQ. So that's the game we've been playing all along, so the yellow stuff, just wiggling something codimension one. So now it's PL, so now the disk bundle has a PL boundary, and so it's a PL manifold of dimension Q. But it's a bundle, so that PL manifold of dimension Q is just, it's got our manifold M as the zero section. So it's PL. So the disk bundle is PL, and this is the simple homotopy type. So it's a PL manifold. This is the simple homotopy type for our topological manifold M. So to put it, make it short and sweet, you put M with a nice disk bundle into Euclidean space, and then you wiggle the boundary so it's PL, and now you've got this PL. The disk bundle is not a PL bundle, but the total space, this Q-dimensional total space, is PL, and therefore triangulated, and therefore a simplicial complex. And that simplicial complex serves, M itself may not be a PL manifold. It can't be a PL manifold, but it's got a disk bundle which is a PL manifold, and that's the simple homotopy type we give to M. And now the last thing to say is if you did this differently, if you did it two different ways, they're going to be, well, the structures are going to be concordant, therefore escobordant, and therefore the same. So there's no issue of the choices that were made here. This is a well-defined. It's well-defined simply because when you pay attention to the choices, you don't change the simple homotopy type. And then the final remark is that if the manifold were PL, so how does this compare? Suppose the manifold were PL already, and you didn't know that. Well then, the PL embedding would already have a PL normal bundle after you stabilize. And so that PL normal bundle, this normal disk bundle, would be, by definition, the simple homotopy type. But when you have a PL disk bundle, it just collapses down to the zero section, and so it's the same thing. So this is how you get a well-defined simple homotopy type for all topological manifolds. This was extended by Chapman to complexes. What did he extend it to? Which one?
Well, compact ANRs.
Yeah.
Well, West actually, it's not quite that.
West.
West showed that every compact ANR has a well-defined simple homotopy type, and then Chapman, using generalizing arguments of Chapman, who proved that every homeomorphism of polyhedra, compact polyhedra, is simple.
Yeah.
So it's a combination, and they used Hilbert cube manifolds,
Yeah.
because this doesn't.
Yeah.
This is
Yeah.
a very good finite dimension argument, but doesn't extend to polyhedra,
Right.
and they used they're clever enough.
Right.
And together, you all solved one of Milner's 7 problems, which
Yeah.
was to establish these kind of things.
Yeah.
And this is all because there is no triangulation. If there was a triangulation, there wouldn't be a problem, of
And there's
course.
no problem.
This-
That's right. So this is, so sort of the philosophy is you've got a topological manifold without a PL structure, then how do you connect it to something simplicial?
That's
Well,
right.
you do it with this
Exactly.
normal disk bundle, and that's how you do it. So that's the idea. Okay. Okay, thank you again.
Thank you.